Welcome back, students. Today we're going to be talking about geometric sequences. In a geometric sequence, the ratio between each pair of consecutive terms is always the same. Now, what that means, this ratio between the terms is always the same. A ratio is usually represented using division. So we're dividing two numbers. Now you'll notice over here I identified 5 as the ratio to this sequence. And that's because as I write the ratios of consecutive terms, that is 5 to 1, 25 to 5, 125 to 25, each of those is equal to 5. So the ratios all equal 5. Now that ratio itself is also significant. By doing my division, going backwards and finding those ratios, I have also successfully identified what I'm multiplying by. 1 times 5 is 5. 5 times 5 is 25. 25 times 5 is 125. So to then find the next term, I am then just going to multiply the previous term by 5, by the common ratio. All right, so in this first problem, we are going to identify whether or not the sequence is going to be arithmetic. Remember, you have a common difference, which meant you were adding or subtracting. If it's going to be geometric, which is going to have a ratio, like what we just talked about, it is going to look like us either multiplying or dividing, though when we write our equation, we're always going to write it as multiplication. Or is it going to be neither? Is it some different pattern altogether? So let's go ahead and check. So if I do 60 minus 120, that would be a negative 60. 30 minus a 60 would be a negative 30. So with me testing for arithmetic, me using subtraction to figure out what the differences are, I do not have a common difference. All right, so that did not work. So next, let's check for geometric. We're going to use division, going backwards, to create our ratios. So 60 over a 120, well, that would be a half. 30 divided by a 60 is a half. 15 over 30 is a half. Therefore, we have a common ratio. This must therefore represent geometric. This is a geometric sequence. Okay, in this next one, let's go ahead and test for arithmetic first. We'll do our subtraction. 6 minus 2 is 4. 11 minus 6 is 5. 17 minus 11 is 6. There's definitely a pattern here, but we didn't get the same number each time. So because the difference wasn't always the same, it's definitely not arithmetic. If I go back and try again with geometric, doing a 6 divided by 2 gives us a 3. 11 divided by 6, well, I don't know what that simplifies into with a decimal, but it definitely does not equal 3. I think it's about a 1.6 repeating. And so, yeah, it's not geometric either. This is neither. Neither of those methods, either finding a common difference with subtraction or finding a common ratio with division, neither of those yielded anything in common. Therefore, it's neither. Okay. Next, let's go ahead and check for our arithmetic. We'll use our subtraction. So 7 minus 3 is 4. 11 minus 7 is 4. 15 minus 11 is 4. By doing our subtractions, we notice we got the same number each time. This is a common difference. So because we have a common difference, this is arithmetic. All right, so now we're going to take this knowledge of finding a common ratio or a common difference to then use that common ratio or difference to find the next terms in a sequence. So over here, as we look at this sequence, it looks like what we're doing is we've got a common ratio. 6 divided by 3 is a 2. 12 divided by 6 is 2. So because my division going backwards told me 2, that means that must be what I'm multiplying to go forward. Multiplied by 2, multiplied by 2, multiplied by 2. So now we continue it. 24 times 2 is 48. 48 times 2 is 96. 96 times 2 is going to be 192. And we've successfully found the next terms in that sequence. Okay, now with this next one, if I try to do negative 16 minus a 64, that'll give me negative 80. And then a 4 minus a negative 16 would give me 20. This is definitely not arithmetic. When I do my subtraction, I do not get the same number. So we should now try for geometric. So using our division, negative 16 divided by 64 equals a negative 4. 4 divided by negative 16 equals negative 4. Negative 1 over 4. Oops, I made a slight mistake. Each of those is a negative 1/4. And the negative 1 over 4 gives us negative 1/4. Sorry, slight mistake. I divided upwards rather than down. So yeah, as we simplify those fractions properly, we notice what we're doing is we are multiplying by 1/4 each time. So now to be specific, we're multiplying by a negative 1/4. So for this next one, negative 1 times negative 1/4 will give us positive 1/4. Okay, now 1/4 times by a negative 1/4. So positive times a negative will be negative, and we're going to get 1/16. Because 1 times 1 is 1, 4 times 4 is 16. Now to continue it, negative times a negative, we're going to get a positive 1 over 64 as we multiply by another negative 1/4. Okay, so find the common difference, find the common ratio, and then if it's a common difference, keep on adding it. If it's a common ratio, keep on multiplying by it. All right. So now, here we've got a geometric sequence. What we are going to do is now graph it. Now to graph a sequence, we're going to have our term number for our x and the term itself be the y. So our first term is a 32, second term is a 16, third term is an 8, fourth term is 4, and the fifth term is 2. So let's go ahead and graph that. So at 1, we're up at 32. Yeah, there we go. At 2, we're at 16. at 3. We're up at 8, at 4. We're at 4, at 5. We're at 2. Now notice the curve that is happening here. We've seen this curve before. This is an exponential decay. All right, and notice how each time the number is half as big. Half of 32 is 16. Half of 16 is 8. So we can keep on taking a half. Half of 2 would be 1. Half of 1 is a half. Half of a half is a fourth. Half of a fourth is an eighth. Then a 16th. Then a 1 over 32. We're going to keep on getting smaller and smaller numbers, but notice that even though the numbers get smaller, we'll never get to 0. We'll never even hit negative numbers. That's going to plateau, and it's just going to get closer and closer to 0 as those fractions get smaller and smaller, but never actually equaling 0. So geometric sequences are the same as exponentials. Okay, the graph is the same. So now let's talk about how to write the equation of a geometric sequence. So over here, we've got that initial one where we started out with a 1, then we went to 5, 25, 125. Now, we started at a 1. That's just our first term. So notice right over here, they're kind of building up our equation. We have our starting number. Then to get to the next number, we had to multiply by the ratio. We had to multiply by 5. So we have our first term that got multiplied by the ratio. Now then to get to the 25, well, we had to multiply by another 5, meaning that we've now multiplied by 5 twice. Or in other words, to get out to the third term, you take your first term and you multiply by the ratio twice. To get to the fourth term, you have your starting number and you multiply by the ratio 3 times. Okay? Notice how that's 1 less. To get to the fourth term, you had to multiply by the ratio 3 times. And that's because we didn't have to multiply by anything to get the first term. We just started with that number. And so then to get out to our nth term, we have our starting number that multiplies by the ratio, and we do it 1 less times than whatever term we want. So when it was the fourth term, we multiplied by 3. If it's, let's say, nth is standing for the 10th term, I want to do 10 minus 1 is 9. I'm going to multiply by r 9 times to get out there. So that gives us our equation. And notice how much it looks like our exponential equation we learned about earlier this year. A times b to the power of x, where once again, x, just like it did with the arithmetic equation, x is just changed to n minus 1. So let's now find the nth term of a geometric sequence. Here they're asking us to find what's the 10th term going to be. So let's first figure out what is happening. We know it's geometric, so I should be able to find a common ratio. 12 over 2, 6. 72 over 12 is 6. Great. So we now know that what we're doing is we are multiplying by 6 over and over. So now I'm going to go ahead and use my equation like they showed up here. So to find the nth term, you take the first term and you multiply it by the ratio n minus 1 times. So we've got a of n. My first term was 2. The 2 then got multiplied by a 6. n minus 1 times. Now, notice they told us up here they want us to find the 10th term. So the 10th term, I'm just going to have to multiply by 6, 10 minus 1, or in other words, 9 times. And at that point, we just need to stick that into a calculator. All right, so we had 2 times 6 to the power of 9. Okay, so we get, let's see, that's about 20,155,092. And we would write that in there. 20,155,392. Okay. In this problem, we see that they are clicking the zoom out button on a mapping website. So if you're on Google Earth, each time you click the zoom out button, we could imagine that this doubles the side length square of the map. So on the side of your screen, you see a certain amount of the Earth. And then when you zoom out, you see even more. So the length of the amount of Earth that you can now see has now increased. It's increasing by doubling. So if the full length of the side of your computer before you zoomed out represented 1 mile, and then you zoomed out, now that side of your screen is now showing 2 miles worth of map. Okay? And so on and so on. Now they do give us a table here. So after the first zoom out clip, the side of our map now represents 5 miles. After we zoom out again, it's now 10 miles. Zoom out again, it's now 20 miles. After how many clicks on the zoom out button does it then represent 640 miles? So in order to figure this out, this would be really helpful if we had an equation to do that with. So let's go ahead and use what we just learned. A of n, our first term is 5. We are multiplying by 2 because it's doubling. So n minus 1 times. Now we want to substitute in 640. So then we get 5 times 2 to the power of n minus 1. So we want to figure out what n would finally bring us to the 640. Okay? So we could do different things here. We could make a table, and we could just continue out our table. We don't know how long it could take. So another thing we can do is to use a calculator. So for this purpose, so that students who are not in class could also use this method, I'm going to show using Desmos. So just go to desmos.com and start that up. So our equation was 5 times 2 to the power of n minus 1. All I'm going to do there is y is equal to 5 times 2 to the power. Rather than n, we'll do x. Oops. Need to get all of that. So x minus 1. Put it in parentheses so that it'll stay in the exponent. So we've got that. Now, for the other one, we wanted to know when it was as high as 640. So notice all I did. I took both sides of this equation, and then I wrote them both as their own separate equations. Okay, and now if I zoom out, what I'm looking for is where my two equations cross, where that blue and the red line cross. And Desmos tells me it's at 8 after 8 clicks. Okay, or like I said, we could have also have continued out that table, just constantly doubling until we figured out how many. 7, let's see, 328, and there we reached our 640. Either method is acceptable. I hope this helps you guys with your work.